Module 2, Basic Instructions and Applications of S7-1200 PLC. In this module, we will learn about the basic instructions and applications of S7-1200 PLC and master the practical application of these instructions through a specific task: the design and simulation of a conveyor belt continuous control system. This task will involve important concepts such as timers and edge-triggered instructions. We will enable everyone to deeply understand the important role of these instructions in PLC control through detailed analysis and design process. First, task description. Our task is to design a PLC-based conveyor belt continuous control system. This system needs to meet the following requirements. First, control the operation of the conveyor belt through start or stop buttons. Second, use timers to implement delayed start or stop functions. Third, use edge-triggered instructions to detect changes in sensor signals. Fourth, implement fault alarm and automatic protection functions. Finally, use simulation software to verify the system logic. This task covers multiple aspects, including PLC model selection, hardware circuit design, component list preparation, installation and wiring, software programming, and debugging. It is a complete PLC control system design process. Second, task objectives. Through this task, we hope to achieve the following objectives. Knowledge objective: be able to master the working principles of PLC timers, TONTOFTP. Understand the application scenarios of edge-triggered instructions, rising edge, falling edge. Familiarize with the design standards for continuous control systems. Skill objectives: be able to independently design PLC ladder logic programs. Configure timer parameters to achieve precise control. Use simulation software to debug system functions. And diagnose and troubleshoot faults. Quality objective: be able to correctly select timer types according to control requirements. Set parameters: IW start signal, PT preset value, Q output, ET elapsed time proficiently, and manually override PT values through the monitoring table, or reset the timer, reset input of the TONR. Third, implementation path. Implementing PLC control projects follows certain patterns. For PLC control of conveyor belts, the implementation path mainly includes the following steps. First, identify the controlled object, namely the conveyor belt motor. Second, determine I/O devices, including input and output signals. Then perform hardware configuration and software programming. Finally, conduct simulation debugging and on-site debugging. This process requires us to comprehensively apply the PLC knowledge and skills we have learned to ensure system reliability and stability. Definition of automatic control and the role of PLC. Automatic control refers to the use of external equipment or devices, such as PLCs, microcontrollers, industrial PCs, etc., to automatically operate a machine, device, or production process, according to predetermined rules without direct human intervention. As the core component of an automatic control system, PLC operates through cyclic scanning, periodically executing input sampling, program execution, output refresh, and other operations to achieve precise control of the controlled object. Task analysis. When conducting PLC control projects, the first step is to identify the controlled object. The controlled object of this project is the conveyor belt motor. Workflow. After pressing the start button, the power contactor Q0.0 and the star contactor Q0.1 are energized and closed. The motor starts in star configuration. After 4 seconds, the star contactor opens. Delta contactor Q0.2 is energized and closed. The motor switches to normal delta operation. If the stop button I0.1 is pressed or the thermal relay contact I0.2 activates, the motor stops immediately. To start the motor again, simply press the start button again or reset with the protective contact when the protection is active. Next, identify the I or O devices, including input signals, start button I0.0, stop button I0.1, and thermal relay I0.2, and output signals, power contactor Q0.0, star contactor Q0.1, and delta contactor Q0.2. In PLC programming, timer instruction is a very important tool. It allows us to create program time delays. S7-1200 PLC has 4 types of timers: the pulse timer TP, on delay timer TON, off delay timer TOF, and retentive on delay timer TONR. Each timer has its specific purpose and working principle. For example, the pulse timer can generate pulses with preset time width. On delay timer sets output to on after preset delay time. Off delay timer resets output to off after preset delay time. Retentive on delay timer can accumulate elapsed time across multiple timing periods until using our input to reset elapsed time. When using timers, we need to select appropriate timer types according to actual requirements and correctly set their parameters. Generate pulse, IN changes from 0 to 1, timer starts, Q immediately outputs 1. When ET equals PT, ET stops timing immediately, Q immediately outputs 0. At this time, if IN is 0, ET returns to 0. If IN is 1, ET holds. On delay timer, IN changes from 0 to 1, timer starts. When ET equals PT, Q immediately outputs 1, ET stops timing immediately and holds. At any time, when IN changes to 0, ET stops timing immediately and returns to 0, Q outputs 0. Off delay timer, as long as IN is 1, Q outputs 1. IN changes from 1 to 0, timer starts. When ET equals PT, Q immediately outputs 0, ET stops timing immediately and holds. At any time, when IN changes to 1, ET stops timing immediately and returns to 0. Time accumulator, as long as IN is 0, Q outputs 0. IN changes from 0 to 1, timer starts. When ET equals PT, Q immediately outputs 1, ET stops timing immediately and holds. Until IN changes to 0, ET returns to 0. At any time, as long as R is 1, Q outputs 0, ET stops timing immediately and returns to 0. When R changes from 1 to 0, if IN is 1 at this time, timer starts. S7-1200 timers can be created in 3 ways. First, drag the function block instruction directly into the block. The background data block for the timer is automatically generated. This block is located under System Blocks and GT Program Resources. Second, drag the function block instruction directly into FB block to create multi-instance. Third, drag function block instruction directly into FB and FC block to create parameter instance. There are several possible reasons why the timer is not counting. First, the timer input must have a level signal transition for timer to start timing. A constant input signal will not start the timer. For TP, TON, the IN input must change from 0 to 1 to start. TOF requires the IN signal to change from 1 to 0 to start timing. Second, timer background data block is reused. Third, only when Q or ET of timer function block is connected to a variable, or when Q or ET from background DB or IEC underline timer type variable is used in program, will the timer start timing and update timing value. Edge-triggered instruction. Edge-triggered instruction is another essential tool in PLC programming. It can generate actions at the moment of rising or falling edge signal transitions. The rising edge and falling edge instructions set the RLO equals 1 when a rising or falling edge is detected at the scanned operand, and hold it for 1 scan cycle. In addition, there are instructions that set an operand on a rising edge of the signal, and instructions that set an operand on a falling edge of the signal. These edge-triggered instructions can help us accurately capture signal changes to achieve precise control of the control process. There are multiple edge detection instructions in the S7-1200 CPU. These instructions can be used to detect rising and falling edges on variables or on the results of logical operation (RLO). Instruction location is shown in the right figure. Scan operand signal rising edge. When a positive transition 0 to 1 is detected on the bit of operand 1 assigned to the contact, the state of this contact is true. This instruction compares the current signal state of operand 1 with its signal state from the previous scan. The signal state of operand 1 from the previous scan is saved in the edge memory bit operand 2. If the signal state of operand 1 from the previous scan, operand 2, is 0 and the current signal state of operand 1 is 1, a rising edge of the operand 1 signal is detected. Scan operand signal falling edge. When a negative transition 1 to 0 is detected at the bit assigned to operand 1, the contact state is true. This instruction compares the current signal state of operand 1 with its signal state from the previous scan. The signal state of operand 1 from the previous scan is saved in the edge memory bit operand 2. If the signal state of operand 1 from the previous scan operand 2 is 1, and the current signal state of operand 1 is 0, a falling edge of the operand 1 signal is detected. Set operand on signal rising edge. This instruction can set operand 1 when the result of logic operation RLO changes from 0 to 1. This instruction compares the current signal state of the RLO with its signal state from the previous scan. The RLO signal state from the previous scan is saved in the edge memory bit operand 2. If the previous scanned RLO operand 2 is 0 and the current RLO signal state is 1, a rising edge is detected. When a rising edge is detected, the signal state of operand 1 will remain set to 1 for one program cycle. In all other cases, the signal state of operand 1 remains 0. Set operand on signal falling edge. This instruction can set operand 1 when the result of logic operation RLO changes from 1 to 0. This instruction compares the current signal state of RLO with its signal state from the previous scan. The signal state of RLO from the previous scan is saved in the edge memory bit operand 2. If the previous scanned RLO operand 2 is 1, and the current RLO signal state is 0, a falling edge is detected. When a signal falling edge is detected, the signal state of operand 1 will remain set to 1 for one program cycle. In all other cases, the signal state of operand 1 is 0. Scan RLO signal rising edge. This instruction can set the output Q when the CLK signal changes from 0 to 1. This instruction compares the current signal state of CLK with its signal state from the previous scan. The signal state of the CLK from the previous scan is saved in the edge memory bit operand. If the CLK signal from the previous scan operand is 0 and the current CLK signal state is 1, a rising edge is detected. When a signal rising edge is detected, the signal state of output Q will remain set to 1 for one program cycle. In all other cases, the signal state of output Q is 0. Scan RLO signal falling edge. This instruction can set the output Q when the CLK signal changes from 1 to 0. This instruction compares the current signal state of CLK with its signal state from the previous scan. The signal state of the CLK from the previous scan is saved in the edge memory bit operand. If the previous scan CLK signal operand is 1 and the current CLK signal state is 0, a falling edge is detected. When a signal falling edge is detected, the signal state of output Q will remain set to 1 for one program cycle. In all other cases, the signal state of output Q is 0. Using TIA Portal software, we can complete the programming of the conveyor belt control system according to control requirements and design program flow. First, we need to create a new project and enter the project view. Then perform hardware configuration, add PLC hardware, and set the IP addresses of the PLC and local computer. Next, configure the PLC properties and enable PLC clock function. Then, define the PLC variables for the conveyor control system design. Finally, according to the program design approach, divide the entire program into multiple segments for writing. During programming, we need to carefully analyze the logic of each program segment to ensure the correctness and reliability of the program. After program writing is completed, we can use simulation software for simulation and debugging. The simulation software for TIA Portal is S7 PLC Sim. It allows us to simulate PLC program operation on the computer, effectively verifying the correctness of program design. Before conducting simulation and debugging, we need to right-click on the top-level project name in the project tree. Select Properties. Select Protection in the pop-up interface. Check the checkbox Support Simulation during block compilation. Task Summary. First, the 3 types of timers each have applicable scenarios. Second, edge-triggered instructions are powerful tools for signal processing. Third, logic verification must be performed before simulation. Fourth, safety circuits should be independent of PLC program. Through timers and edge-triggered instructions, the design and simulation of conveyor belt continuous control systems can be achieved. Thank you for listening.